Hello, we are Group Infra Green. We are presenting for CEE159. Our group project is titled is Heavy Metal Removal from Long Beach Stormwater. Our team members are Sterling Butler, Olga Godino, Kelly Holman, Taylor Logan, Natasha Marsden, Aiden Metzner, Andrew Todd, and me, Carla Vargas. So our study area, we chose the Lower West Side of Long Beach between the 103 freeway and the LA River. We chose this area because of its high industrial activity. Some of the industrial activity includes aircraft and automotive manufacturing, metal fabrication, glass fabrication, and other types of manufacturing. Such operations often release toxic heavy metals in stormwater runoff, and this runoff will go directly to the LA River and to the ocean. As we can see in the picture there with the red box, that's our area of interest, and we can see the LA River to the right and the ocean at the bottom. This is an area of concern because there isn't that much green infrastructure to reduce heavy metal pollutants. And for this project, we'll introduce two solutions to reduce the amount of heavy metal pollutants going into the ocean. This area is 1.38 kilometers squared and receives around 30.55 centimeters per year of water in the form of precipitation, according to the average of the last 20 years of data from the LA hydrologic reports. And Andrew will present the TMDLs in this area.
So area, the part of the LA River, which is adjacent to our area of interest, is right at the end of the LA River. And so in the 2016 EPA impaired water reports, they found very high concentrations of heavy metals, particularly cadmium, copper, lead, and zinc, a lot of which came from this industrial area we're looking at directly adjacent to it. And so when we were designing our systems and doing our calculations, we assumed that the concentration of these heavy metals in the stormwater runoff from our area was the same as the impaired waters concentrations that were reported by the EPA, which can be seen in the table. Next slide. And so the two solutions that we looked at designing for our area, the first one was a permeable pavement with sodium titanate substructure like inside of it. And so that removes heavy metals from stormwater very well through ion exchange. So these heavy metal will replace the sodium in the sodium titanate and will be absorbed into it. And then the other solution we were looking at was a more typical stormwater biofiltration system, which would remove heavy metals from the stormwater by absorbing into the soil, as well as some minor plant uptake.
So as Andrew had mentioned, the first solution that we had investigated was a permeable pavement system that would consist of a sodium titanate infused within its mixture. After investigating a couple different types of permeable pavement, we decided to choose porous concrete for its ability to handle low impact traffic within this area. And it has an approximate infiltration rate accounting for potential debris that would be running over this area of 16 centimeters per hour. Using linear measurements of the area of focus, we determined that there was around 0.26 square kilometers of pavement that would be retrofitted with this solution. And using a conservation of mass function in the graph up in the right corner, with varying precipitation flows coming in throughout a year, we determined that these heavy metals would ultimately have a removal capacity of 75 to 95% within this system. And these were estimated with the reaction rate coefficients found in a paper that was doing a similar study on copper, zinc, and lead. Looking at the graph to the left, This is a linear regression of the depletion of sodium titanate through this ion exchange. If we were to implement the system over a 40-year period and accounting of with the counting of a factor of safety of about 2, unfortunately, as can be seen with the very large number at the bottom, implementing such a system, or even just for the cost of materials for a porous concrete and sodium titanate slurry, it would cost upwards of $15 million. This is very expensive, we understand, but we'll be talking about this cost effectiveness a little bit later. Next slide.
And so for our biofilter system, we found that our area of interest has a very high percentage of impervious surfaces right now. And so we found from literature review that oftentimes for areas like these, we want the size of the biofilter to be about 2.5% of the total catchment area. And so for our catchment area of 1.38 square kilometers, that comes out to over 30,000 square meters of biofilter, which is we can't implement it as a single large biofilter. And so we found that it was much more effective to spread out a bunch of smaller biofilters. And so when we were analyzing it, we assumed an approximate area of 250 square meters per filter area. And the locations of these biofilters we want to put next to highly frequented roads like West Anaheim Street and Santa Fe Avenue, as well as directly next to the LA River, which has lots of open space. And then, so for the vegetation area, we consulted the Southern California LID manual for native plants that are effective in bioretention and biofilter systems. And we found that plants such as Pacific wax myrtle and mugwort and island alum root would be effective in our biofilters, as well as we could utilize some of the soil already in the area, which is categorized as METS or PICO soil by the National Soil Survey. And it's good because it has very high hydraulic conductivity, but it doesn't always have high enough organic carbon content for our uses.
So because LA is a pretty water scarce area, we really wanted to implement this biofilter to be able to collect the stormwater for reuse rather than allowing it to exfiltrate into the surrounding soil. So we'll be implementing a liner as well as a raised outlet, and then using collection pipes in the drainage layer to direct the water into the existing stormwater system in the Long Beach area. And then other than that, the layers of our biofilter is pretty typical of any other biofilter. We'll have a pre-treatment zone with rocks, vegetations, and grades to prevent larger sediments from entering the system. We'll have all that native vegetation that Andrew just talked about in the ponding zone, as well as about 50 millimeters of organic mulch, which will help bring up that organic carbon content that we're lacking in the existing soil already. And then we'll have the filter media, which does the majority of the actual removal of heavy metals, especially. From a literature review, we found that a filter media consisting of about 80% amended sandy loam, which is present in the existing soil there already, like Andrew just mentioned. So we can use some of that as well as 10% vermiculite and 10% perlite by volume. And then we'll have a transition layer to prevent things from making it down into the drainage layer of the system and prevent the mixing of pollutants in there. And that'll just be a layer of coarse sand to prevent it from going into the drainage layer, which will then be collected through the collection pipe, stopped by the liner from exfiltrating and go into the existing stormwater system. Next slide. And then in terms of the cost analysis, like Sterling mentioned, the porous concrete system is pretty expensive to implement in this like already very industrial, very developed area. And so for that reason, the biofilter or the many biofilters would be a lot more feasible to implement in this like very much developed area. So we can put those smaller biofilters alongside the LA River and alongside those like large impervious pavements, those big roads, and place these biofilters in places that stormwater naturally flows in the area. The cost of a large biofilter is estimated to be about $500 per meter squared, which comes out to about $125,000 for a single biofilter. Both of the systems we analyze are extremely effective at removing heavy metals. They both have some downsides in terms of other pollutants, like nutrients can be a bit of a problem in biofilters like phosphorus and nitrogen. And so that's something we looked at improving the removal of in biofilters, but overall both were extremely effective in our primary goal, which was removing heavy metals.
So to summarize our main finding that Natasha had just gone over, clearly biofiltration would be the most cost effective in achieving our goal of removing high removals of heavy metals. Some of our biggest observations sort of about this project as a whole. The first one is point versus non-point source removal. With this permeable pavement system, the goal was to try and tackle this heavy removal at the source of where it's coming from, whether that's the traffic from the scrap metal yards that are in this area, the auto industry, any other traffic flow, things coming from cars and whatever that's traveling in this area, trying to find ways to, during the wet periods in Long Beach, remove those heavy metals before this water enters the LA River or moves through the stormwater systems. While bioretention systems focus more on collecting that water from a certain area and achieving mass removal at the same time. So if we were to think about scaling this beyond an area of 1.5 square kilometers at such high cost for a permeable pavement system for a small area, it would be much more economically feasible to focus more on sourcing all of our water to the same area for any sort of water treatment. The second thing that we didn't really get a chance to talk about or investigate in our study was the maintenance of such systems. With both adsorption and with ion exchange, the fact of the matter is that these heavy metals will still be present within these filtration systems. So the question becomes, once we collect these heavy metals, what do we need to do to either pull these filter medias out and extract these heavy metals, or can we somehow control the flow that's moving through these systems to collect these heavy metals and dispose of them properly? Lastly, just thinking about the future of industrial parks in general, Long Beach is not the only area that has high levels and high traffic of industrial work. The sad thing is that a lot of these areas don't have a lot of investment that's going into the way that water is moved and ultimately filtered through, because they're so focused on whatever activity is going on within this industrial area. And we realize that there's going to need to be a lot more discussion between what industrial facility and certain green infrastructure powers to find ways to better source this water and better filter this water. And that's our presentation. So if there are any questions, feel free to ask them, but thank you for listening.
Perfect. Any question from students? You guys can write the question in the chat window, or if nothing else, you can clap using the symbol like I just did, because they spend a lot of time, like you guys, working on this project. Particularly, this one was very adventurous projects because they use materials that's normally not used for stormwater treatment. So I knew from the day one that it's going to be expensive. But it's important for them to find out or find an alternative way where it cannot be expensive. So like you conclude, if you just spread that materials throughout the entire place, it's going to be expensive. But if you collect all that water, let it pass through a filter which has these materials that you replace time to time, it's going to be much cheaper. So I think that's the important conclusion. So that means stormwater routing is major part of this design here. And then you can perhaps store in a underground tanks and then let it filter through that system with time and before it discharged. And so it's possible that way. So it's not really bad things. But I would suggest that think of this, because we are presenting in new materials. So this is nothing with this class presentation. Imagine this is your startup, something that you are going to present to the LA County. So a couple of things to narrate this presentation is to start saying that these are industrial area, these are the economy of this area, and they pollute. So it's always they are charged with these treatments all the time. They are paying extra money to treat that water. So how about having a solutions where it continuously work for them? And then you present what the current solutions are. You say that, look, these are the solution right now, but still that doesn't meet the TMDL. And so what we present here is the new materials, which are expensive, but it can be used to reduce the cost over time. And then you say, what is titanate, sodium titanate? Because that's something you need to explain, because nobody would have known what does that mean, where it is used, because it's toxic, is this bad? So for instance, you can say that titanium dioxide is something that people use in the sunscreen. So if it's toxic, people not apply, right? So that means there. Then you say sodium titanate has the similar structure. So it's just a ion exchange regime that remove any metals and release sodiums. So sodiums are pretty non-toxic, because when you eat salt, that's the sodium, right? So that means non-toxic. So you have to present, break it down to something more presentable form. And once you say that, then you say, okay, this is our design. This is what we do it. I think like last group, you can make big locations and highlight the area where you are going to present, where you want to install. Making those shaded areas is just visually appealing. And then you say, this is our calculation. This is our assumption. This is our calculation. This is how it would work out. So I think, it's just the story. When you tell story, you got to tell in a perspective of the problems and why your solution could be something interesting. Okay, so that, I think that's all my comments just for your own practice for next time you present to industry. But overall for the class, this was great.
Thank you, Professor.
So I'm going to stop recording.